So what I wanted to start with here was to talk a little bit about technologies, but why do I want to focus on technologies? And it's because when we as architects try to come up with what we think an exascale computer should look like, or how we should be architecting an exascale computer, just like architects that build houses, we have certain building blocks that we can use to get there. We have the advantage within Intel also of developing some of those building blocks. So it really allows us a level of sort of co-design where we're not only taking building blocks as given to us, but we can actually influence those building blocks. So I think we're really at a very exciting time right now because, if you look back at, if you look at the calendar, we're 2017, almost 2018 now. And as you've probably seen in the press, the DOE and other countries are all shooting to hit exascale in 2020, 2021. It's only 3 or 4 years away. So for us to hit exascale in that kind of time frame, that must mean 4 years. We already know how we're getting there. So we've been thinking about getting to exascale and the efficiencies that means. And it's not all about exascale, of course. It's about building systems that have that kind of capability, that kind of cost performance, and that kind of energy efficiency so it can be scaled to all levels. But for a decade, we've been thinking about this. And if you had asked me probably 5 years ago, we knew the challenges, right? We've been coming to conferences like this and talking for probably a decade about the challenges of exascale and trying to find solutions. And the reality was we knew we had the challenges, but we didn't necessarily have the solutions. But I'm very excited that we actually do now see our path to there and beyond. And we think we actually have an architecture that will not only get us to exascale, but will really get us to an exascale, highly usable exascale type of system in all the smaller systems that it implies, and also lay the groundwork for things behind that. So I think we're in a really exciting time, but a lot of this has happened because of the technologies, right? If the technologies didn't advance to enable us to do this, we wouldn't have done that. So I thought I'd spend a little time talking about some of those technologies. Let me start with silicon photonics. So, silicon photonics is really fundamental to us being able to get to the kind of performance, right? It's one thing to have a lot of compute, but if we can't connect up processors with the right kind of cost performance from a connectivity perspective and the right power, we really can't do it. So there's been an enormous amount of effort over the last decade. It's continuing now, and we still have a ways to go, but there's a lot of activity in really developing this new technology and moving it to the next level. So we're on this very fast ramp right now with respect to silicon photonics. We're starting with sort of linear type physical devices, and it'll be moving into ring devices, which have much higher, much more cost effectiveness because of the size impact of that, and then eventually into the multiple wavelengths. And all of these things, what it means is we can pipe enormous amount of bandwidth down a fiber, and so the cost of the connectors, the cost of the fibers, all of that starts to get, you get multiples of, you amortize it multiple times because of the kind of bandwidth that we can get through them. And that's really needed for us to go to the next level, especially as we get to exascale and we look beyond. These are really critical technologies. This just shows you how important it is in some sense and why we in computing sort of have a somewhat unique challenge. So the blue line here represents the worldwide bandwidth of the internet. So this is all in the whole world. This is all the bandwidth that comes out for the internet. And the single little orange dot that you see there is the one supercomputing system at that time, and the amount of optical bandwidth running around in that single system. So you can see that supercomputing really is driving the communication capabilities, and obviously to do that you have to do it in a very cost-effective way. And I've worked out, I looked to see where we are now and where we're going, and what we see is there's another about factor of 10 over that we think we're going to have in an exascale system. So we'll continue to be well above this line. As fast as that global internet connectivity is rising, supercomputing still has needs that really swamp the kind of bandwidths that are running around worldwide. So it really it's an interesting scale of what we're really, the kind of communication. Data centers are similar. There's a lot of bandwidth inside the data center, but when you talk about how we're really connecting the world, it's still far, far lower than what we do in systems. Another technology that's really exciting, and this really offers really a new dimension to systems, is the new memory technology. So 3D XPoint is a new memory technology that we've developed, and what we have here is really a fundamentally new memory technology. It's been a long time since there was any fundamental new memory technology that can be used, and it's sort of in between memory and disk, and that really opens a whole new dimension of how we can utilize this. But for us to utilize this effectively, it needs to have the right software to do it as well. What we're finding is now we can put this into systems and have I/O systems that can be orders of magnitude faster than what you could ever have done, even with a flash device, but also obviously with respect to a spinning disk. So when that starts to happen, we need to have the right software interfaces and the right to do that. And we're all, we've been very successful with POSIX type file I/O, and that's been the sort of the cornerstone of how we handle data or large scale data. And what we find is that we now have an opportunity to move that data around much faster than we ever could before, and it means we need to rethink this to take advantage of these kind of technologies. Another technology that's really come into its own now and is really fundamental to us being able to reach the kind of performance capabilities that we'll want in systems is high bandwidth memory. So the high bandwidth memory offers us a very different trade-off. Even though it's still DRAM, it's a very different trade-off of capacity to bandwidth. Literally, sort of the ratio of capacity to bandwidth is almost 2 orders of magnitude higher than what you would find in a traditional DIMM. And that ratio means that we now have enormous amounts of bandwidth, which we need, of course, to support the compute. And this whole concern about the memory wall, which is also one of those challenges that we were talking about for the last decade, is something that we were sort of at the same kind of bandwidth to compute ratios as we had a decade ago or more. So it's actually a great story, but it comes with its own constraints, of course. All these new technologies have constraints, and one of the constraints is the way we get the performance is to tightly couple it to a processor, but that tight coupling means it needs to be fairly close, and that proximity limits how much of it we can get, hence why we want to stack it, right? Stacking it allows us to put more capacity close, but you can only stack so high. And so in the end, there's a finite amount of capacity that you can actually get into a socket with a processor, but you end up with this very high density solution, but with finite capacity, still significant, but finite, and you want to find a way to utilize that and utilize all that bandwidth opportunity. And this is when you think about, one of the things I want to try to get to here is to give you some idea of when we think about what systems are going to look like in 4 years, to give you some idea of what it's going to mean to you as a user. How should you be thinking about it when you have choices of how you move your algorithms or map your applications. It gives you, hopefully this will give you some idea of some of the constraints and some of the opportunities that you'll be seeing in those future systems, but also ways of really optimizing code is similar to what we're doing today, but there will be opportunities to get much more performance if constraints such as this are taken into account. So what this amounts to is that really, if you can architect your application to be able to get much more performance per memory capacity, basically reuse that data in a more effective way somehow at a very coarse grain, we're talking about at the gigabytes level, then that can drive a lot of performance. We have much more performance that we can get out of it in that domain. So obviously the processor is a key element here as well, and what you see today is you really do see this diversity of different compute opportunities and directions that we're going. And really part of this is really focusing on having those special purpose things like Gadi mentioned that are really targeted for a particular, like a deep learning application where you want to build something, there's enough volume there to build something that is really fully optimized for that. And then there are other more general solutions, as you know, Xeon-Phi, et cetera, that can cover the overall space. So we really do have this large diversity of silicon that is coming out. So this, when I talk about storage here, I'm sort of mapping to the longer term future when I see that the kind of bandwidths and opportunities that we have are opening up a new dimension. And so when we look at sort of when we start from the left here and we have a sort of the compute nodes attached to a fabric, and then the fabric would go off to the other compute, and you have sort of node local storage connected to that. That's sort of the way we do things at small scale now. As we move forward, we see that we want to try to get to a mode where we really have globally addressable storage, where the capacity of that local storage, we want it to be globally accessible and addressable. So in a common namespace, so that we have we move to this model sort of on the right or in the middle where we have disaggregated storage, where the storage can be spread throughout the machine and we can take advantage of the kind of bandwidth opportunities that are there when we do that. There's a lot of challenges to this, but a lot of upside too when we can move to this model. So this gives you, when I talked earlier about how do we, how can we take advantage of much higher bandwidth in things like 3D XPoint or even the 3D NAND, even when when the cost per capacity of 3D NAND gets to the point where you can build entire storage systems out of 3D NAND, suddenly you want to do things potentially in a different way. So we've really been looking at trying to architect a software stack that was really co-designed from the ground up, taking into account not the constraints of a spinning disk, which is sort of how the standard POSIX kind of I/O and file system stack was developed, thinking about those constraints. Now we're looking at taking the constraints of non-volatile memory and say, what would we do from a software perspective if you wanted to fully utilize this kind of technology and get the most performance that you could? So we've been looking at this software layer, Deos. Some of you are probably familiar with it, where it really allows us to get that kind of new performance, but through a different I/O layer, where we really do objects as opposed to files. So jumping ahead a little bit, so Jim Held's going to give you a talk tomorrow. It's going to be exciting. So about some of the things that Intel's doing much longer term, and some in terms of both quantum and neuromorphic. And I just wanted to give you a little teaser here about it. But there's, neuromorphic is getting more and more visibility and lots of activity around really the opportunities that we could see there. So we've been working on trying to develop this ourselves, and I think you've probably seen some of the press releases on this. But the goal here really is to be able to do some of those things that we look at with deep learning or machine learning, and trying to do some of those with much more energy efficient models. So and we're trying to bring ourselves up to be able to do this and integrate these into the systems in the future. And I'll talk a little bit about that more as I go. So quantum also obviously in the news, lots of things trying to get more and more qubits and trying to do this efficiently. Obviously Intel, one of our roles in this is really focusing on the manufacturing side of this, trying to look at it and see how can we partner with others in trying to make qubits a reality and allow this technology to scale. Again, sort of a fundamentally new architecture level. It's in the future for sure, but it's not in the immediate future in terms of large-scale systems built out of it. But obviously, there's a lot of interest in it. There's been some success recently in sort of trying to map algorithms like quantum chemistry to quantum computing, and we're continuing to try to look at that and understand what are the limits here and how far can this really go. So I want to talk about some of the driving forces here. So one of the key forces, and Gadi talked about it, is really trying to, when we think of an exascale system, we don't think of an exascale system now as a system that's really optimized only for traditional modeling and simulation. It really is, we're really viewing it as that there's really sort of three pillars, and we're all first-class citizens, right? There's the AI, the analytics, and the modeling and sim, all first-class citizens. And so we're trying to build a system that really has the capability of handling all of these. So that's really when we look at what are we trying to do. In fact, this is sort of the requirement that not only we want to do this, but this is what we're hearing from you. That those algorithms, the algorithms that might have been developed for other purposes, are being useful, just as Gadi was talking about in the traditional modeling and simulation. Some of those algorithms that we used in AI are starting to be used there. So we need to make sure that we can do a great job on those as well. So power remains a challenge. Again, this is one of the things that we've been talking about for a decade, that this is a huge problem. And I have here a chart that just kind of shows you that there's always been this focus, well, how do we get to more energy efficiency? We have the big cores, which are great at complex control flow type of algorithms. And we have the many core, the kind of Xeon-Phi, and we have the tiny cores, which would go even more extreme. And they have different energy per operation scales. But what happens here is if we build a whole system out of tiny cores, we know that puts an enormous load on the user, since now your single thread performance drops, as you can see, enormously, like 10x. And you will get the 3x energy efficiency perhaps compared to a big core, but only at the core level. So there's always the threading inefficiencies and the scaling inefficiencies, and by the time you roll that together, unless you pay really put a lot of effort into it, you'll lose some of this energy efficiency. In some cases, you lose all of the energy efficiency through that process. So we're really we realize that we really need a balance here. There's going to be a need for those cores that can handle those complex segments of your code. But there are parts of the code that do have this enormous amount of data level parallelism where we really can exploit it in other ways. And so this idea of really finding a way to accelerate those is one of the key focuses that we're that we have been focusing on. So some of the key learnings from the past. So, the complexity of workloads and the Xeon processors, they really remain the workhorse. As you're well aware, if you look at the top 500, it's still primarily standard Xeon for good reason. It's the barrier to move your code to something else is high. And so what we really want to do is to make sure that we have an architecture that can continue to handle those traditional workloads in a very efficient way, but then open the door to really exceptional performance and when we utilize these new techniques. So we also know that the old algorithms are changing slowly, but then the new algorithms really do bring different balance points, and deep learning is obviously an example there. The other thing is when we do add new architectural features, sometimes we as architects look at them and think this has great, if you just did this, if the users just did this, it would solve all the problems. And in some cases it will, right? When you do the work, it really will. But it's been difficult to get the whole community to move to that when it means users actually getting and doing work and basically becoming computer scientists as opposed to the application owners. That's where we've always had a problem. And we can get over that hurdle when there's a big gain to be had. So the barrier's high. Not that it's not that we shouldn't go there, but the barrier's high. So we want to make sure that when we do push some of this effort onto you, the user, that the opportunity and the value prop has to be high enough to do that. So let me talk a little bit. I don't have a whole lot of time left, so I'm going to go fairly quickly. But when we look about future directions here, I think of it as really building a system that has a lot of flexibility, because there are all these new technologies coming on, and when we think of neuromorphic and so on, all these things are coming on over time. And so I want to be able to have a system that can take these new technologies, even have late binding into the system if necessary, or upgradability, that we can put these new technologies into the system and build a balance that works for you. So that's one of the key concepts. So, there's a lot of architectures, and so one of the things about HPC, of course, especially at the high end of HPC, it really is sort of the incubator of lots of things and really the testing ground. So you see architecture sometimes that we come out with that appear to have similar capabilities or appear that they can handle both things, but then they have somewhat differences in terms of other domains. And so, but there's some overlap in the application space that they would have, but that's really intentional, that we really do want to do this so that we can explore the overall space and make the right decisions. So, we're really looking at, so when we look at what are we doing for the future, what are we really doing for Exascale, obviously I can't go into a lot of details, but we're looking at really making sure that data level parallel, both coarse and fine grain. So fine grain down to thousands of cycles, coarse grain to seconds, that we can do both of those exceptionally well. So when you have that kind of parallelism, we can exploit it. Energy efficient acceleration is really key here, right? Is to be able to do that acceleration. If we can't do it in a more energy efficient way, then it's in the end not going to work, right? We still do have that energy challenge. By the way, energy efficiency and compute density are often related. So the more energy efficient the compute can be, often it's higher compute density as well, and therefore more cost effective. So fortunately, they are highly correlated. Predictable execution, so trying to exploit the reality that a lot of applications and a lot of algorithms are highly predictable in terms of how they access memory, how they take branches, et cetera. All the things that we've done in the past, kind of taking that to the next level and utilizing it and recognizing it to get even more performance. Integrated fixed function. So as we look at algorithms and we find areas where, we've done this before, right? Vector units, even original floating point units were really put on there because we recognize that, a floating point multiplication, we shouldn't do that as a bunch of integer ops anymore. We should build a unit called a floating point unit and use that to accelerate floating point code because it happens a lot. Well, so those same concepts we're doing that at more and more the meta level. Gara mentioned tensors, for example. Matrix multiply, seeing it more and more often. Having a unit that can do a matrix multiply efficiently seems like a pretty straightforward thing. As our transistor density increases, we can afford to spend silicon on that. General purpose data flow. So we're seeing that all of these accelerators, when you take them apart, when you pull them apart, even if you think about a floating point pipeline, when you pull it apart, what it is a data flow. It's a data flow, and trying to do that in a more general way can give us a lot of benefits. So when we look at the targets and what are we trying to do, just a couple of comments on this. So, trying to get to an exaflop, we think we can get there with these kind of parameters. So it's very exciting, and if you look at these, well, these are all, the 50x, the performance of the 2012 systems, which is sort of the target of the exaflop, right? That's a more fair exaflop than just saying exaflop. Saying 50 times the performance of the machines that were 20 petaflops seems like a good way to describe it. And you can see we're from a metrics perspective, it looks pretty good from a 50x. The one thing you see here that isn't, besides the power, which hopefully isn't 50x, is the memory capacity, right? So you see that the memory capacity is not growing at that rate, and that's because to get to the kind of bandwidths that we need to use this other memory technologies that really are highly integrated, and it's limited in the amount of capacity. So that's both a cost and just a fundamental constraint from a physical packaging perspective. But that brings us back to how do you really utilize these kind of machines? So you're going to have the kind of bandwidths that you want. You're going to have the even on the fabric, I don't have the number here, but bisection, we're thinking we can get close to the 50x in terms of bisection kind of bandwidth numbers. But the memory is the constraint. And this is normal. This is not talking about the I/O or the 3D crosspoint or the 3D NAND, which also offer new opportunities, but this does, the standard memory is what this is referring to. And then we have that opportunity with the non-volatile memory, which is sort of wrong color here, but the bottom line, huge amounts of bandwidth to non-volatile memory that we never had before. So, but when I say we want to try and build a machine that can work for all these different domains, we have to look at it also from a software perspective. So really trying to build a software environment that allows the machine to be able to use it in all these modes. One of the things about these different domains is that they do have different software models. They use the hardware in different ways, right? We have different frameworks that are used in some of these versus HPC, which will tend to write to the metal and use standard MPI. So we're trying to really unify those three pillars and come up with a unifying, but also one of the key things here, going back to what I said earlier, is rather than thinking about your data moving in and out of disk, really trying to do this now more at a memory level or at that much faster I/O level than what we currently do. So what does this mean for the user? So we really are trying to come up with this coherent view that the same software stack can be utilized to run all of these different workloads, and we think that's going to be a real enabler to getting performance out of this. We also, by utilizing that locality of a non-volatile memory with enormous bandwidth, as opposed to going off machine to a spinning disk, really allows us to avoid some of the data movement, helps with performance, power, lots of other things, and also to have a scheduler that has to be aware of this. And then I talked already about this DAOS and trying to move to an I/O software paradigm where we don't think only in terms of POSIX, but we open up a new dimension where we think in terms of objects, so we can really take advantage of, and DAOS is just one of the examples, but trying to really be able to exploit the opportunities that this new memory technology offers. The last thing that I already mentioned before is really trying to make sure that we, from a user perspective, if you can take advantage of get more performance out of the same memory capacity, we will have the system infrastructure to allow you to do that. And so in conclusion here, so new and emerging technologies are really important and are enabling us to get to exascale. We think we have clear line of sight at this point to get there. We think that these systems will have both excellent legacy potential, but also open up a new dimension to get even much higher performance. And I talked multiple times about computation per memory being a key thing here. And while I've been talking about exascale, it's not obviously all about exascale. Exascale is one machine. We're trying to build an architecture that can be used at all scales, right? So this will mean racks, multi-petaflop scale racks at reasonable cost and power levels, which will really change the game, we hope, in terms of what we can accomplish with these systems. And system software and user applications will, they'll continue to to have the opportunity to stay on this course. So we really do see this opportunity, you know, of when you see the top 500, that exponential curve is going to continue for a while, which is really good news, I think, for all of us. And, you know, from a power perspective, you know, looking at a TCO model, what I see is a lot of systems that you use are liquid cooled, and that does get us more efficient solution. We see over time, I see over time, the importance of keeping the junction temperature low. Things that are easier to do with liquid cooling will pay even more dividends over time than it does now. So the difference between air and liquid is going to even increase over time, I think, in terms of the cost performance window or change that you have between those. And the convergence, last point here, is really the convergence will result in machines that are more flexible, more easily configurable, and hopefully can really leverage some of the learnings, right? We get great benefit from getting learnings, as Gadi mentioned, from different domains and bringing those in and helping sort of even traditional simulation. That's it. Thank you.